So here's a few examples of things that we don't actually have to, well, the top things we don't have to calculate because they're zero, because sine of x is an odd function. What does it mean to be an odd function? It just means that essentially the right side, the side right of the x-axis, or sorry, y-axis, and side left of the y-axis, kind of do the opposite things. So sine of x from negative pi over 2 to pi over 2 specifically, sine of 0 is 0, sine of pi over 2 is 1, sine of negative pi over 2 is negative 1. So the graph does this kind of deal. And what happens is this area here is counted as positive, and that area cancels out the area here that's counted as negative. So when you integrate an odd function from the negative number to the corresponding same positive number, the area on one side is going to cancel out the area on the other side. And if we do this, right, if you actually calculate this, the antiderivative sign is negative cosine. You get negative cosine x between negative pi over 2 and pi over 2. And cosine of pi over 2 is 0, and negative cosine of pi over 2 is also 0. So you get negative cosine of pi over 2, which is 0, minus negative cosine of negative pi over 2, which is also 0. You get 0 minus 0, which is 0. The same sort of thing is true for 4x minus x cubed. If you set 4x minus x cubed equal to 0, if you factor out an x, you're left with 4 minus x squared. If you factor out, if you factor this further, you get x times 2 minus x times 2 plus x. You definitely have intercepts at negative 2 and 2 and 0. So the graph of this looks like the following. It looks vaguely like the following. A negative 1 and b. Darn it, I wanted the other function. Sorry, I'm going to change this just slightly. Just because I want it to look slightly different. It's still going to be essentially the same. It's going to have the same intercepts. It's just going to be x cubed minus 4x. So, right, so the factoring would then be, sorry, x times x squared minus 4, which is x times x minus 2 times x plus 2. Okay, so the graph of this one looks kind of like this. It intercepts at negative 2 and 0 and 2, and it does this kind of deal. And it keeps going. And again, since it's an odd function, and we'll talk about what it means to be odd in just a second, right? This area here being positive is going to exactly cancel out this area here, which is counted as negative. And if you do the integral here, you get the integral of x to the 4th over 4 minus 4x squared over 2, which is 2x squared, from negative 2 to 2. And here's what's going to happen. When you plug in 2, you're going to get something, right? You're going to get 2 to the 4th is 16 over 4 is 4, minus 2 times 2 squared is minus 8, minus, but then when you plug in negative 2, since all the powers here are even powers, you're going to get the same thing whether you plug in a positive or negative. So when you plug in negative 2, you're going to get negative 2 to the 4th, which is 16 divided by 4, which is 4. And then minus 2 times negative 2 squared, which is 2 times 4, which is minus 8. But this is negative 4 minus negative 4, which is 0. So when you've got an odd function, the area on one side is always the opposite of the area on the other side of the y-axis. And let me erase these for a second, because these are more even functions. We'll deal with in a second here. But generally, like, if you have the integral from negative a to a of a function x, if we know that f of x is odd, then this is equal to 0 every time. And how do you check to see if a function is odd? F of x is odd if f of negative x is equal to negative f of x. Or as I like to think of it, right, if you take, like, for example, in this function here, if you look at f of 1 is equal to, let's see, if this is my function f of x here, f of 1 is going to be 1 minus 4, which is negative 3. On the other hand, f of negative 1 is negative 1 cubed, which is negative 1, minus 4 times negative 1, which is plus 4, which is positive 3. So we see that f of negative 1 is equal to negative f of 1. It's an odd function. Now, I should mention, showing it for one particular value of x doesn't actually justify that it's not a function. To actually show this function is odd, you would take this function and you would plug in negative x. So f of x is x cubed minus 4x. F of negative x is negative x cubed minus 4 times negative x. And then we're going to get negative x cubed plus 4x. And oh, look, that's the same as negative f of x. So, oh yeah, for real, f of negative x is equal to negative f of x. So f of x is odd, which means this integral from negative 2 to 2 of this odd function has to be 0. Okay, we'll deal with even ones in a minute. So what I really want to get at is there was a homework question, I think like homework question 19 or 20. I think this is the second one where it's an odd function. So they tell you something. They tell you the integral from 0 to somewhere of some function is equal to some number. And the key observation that you have to make to be able to do the rest of the problem is to know that this is odd. So this function here, which I'm going to call g of x is odd. Let's check that. If we look at g of negative x, that's going to be a thing. And let's look at negative g of x. So g of negative x is negative x quantity cubed times the square root of 9 minus negative x squared. Now none of the x, I'm not integrating that, just simplifying it. So that's going to be negative thing cubed is still negative times the square root of 9 minus x squared. By the way, if you guys have questions, throw them in the chat or whatever. Other than negative of the function, you're just putting a negative in front of the whole entire thing. Are those the same? Yes, they are. So g of x is odd. So here's what we know. We know for sure that the integral from negative 3 to 3 of the same function is 0. Now, the questions that were asked are the following. So that's actually one of them. Right, so they ask us to find the following things, or somewhat like the following things. So we want to find the integral from negative 3 to 0 of x cubed times the square root of 9 minus x squared dx. We want to find the integral from negative 3 to 3 of x cubed times the square root of 9 minus x squared dx. And then we want to find something like the integral from 0 to 3 of, let's say, 10 times the square root of 9 minus x squared dx. Okay, so before we get going here, I actually want to show you the picture of this. So let me show my screen for a second. Grab this here. Yeah, give me the thing. There we go. Okay. Yes. So here is the graph of that function. This is the graph of y equal to x cubed times the square root of 9 minus x squared. And if you look at it, the area on the right side, right there, is clearly the same as the area on the left side down there, except they're opposites. So this area here is getting counted as positive, and we were just told that area in red is 162 divided by 5. So that means that we know for sure this area in green has to be the negative of that. That area in green is going to be negative 162 over 5. There's no question about it. But that area in green is totally the integral from negative 3 to 0 of this function. So we can say right off the bat, the integral from negative 3 to 0 of the same function has to be negative 162. divided by 5. Another way you can think of it, which we'll actually see in this next part here, I'm going to stop sharing for a second, is that this integral here we know has to be 0 because it's an odd function. And you can think of this integral from -3 to 3 as the integral from -3 to 0 of x cubed times the square root of 9 minus x squared dx, plus the integral from 0 to 3 of x cubed times the square root of 9 minus x squared dx. But we know this is 0. So, and we know that this here is 162 over 5. So since that's 0 and that's 162 over 5, this has to be what cancels that out. That has to be negative 162 over 5. Finally, this last one is just factoring out the 10. So when you have an interval of a constant times a function, you can factor out the constant. So that's 10 times the integral from 0 to 3 of, oh, I forgot the x cubed there, sorry, of x cubed times the square root of 9 minus x squared dx. And then we end up getting 10 times, well, we know that this is 162 over 5. So we get 10 times 162 over 5. 10 over 5 is 2. 2 times 162 is 324. Excellent question. If a function is odd and you show that it's odd, can you write the answer as 0 or do you have to integrate it? And the answer is you do not have to integrate it. In fact, specifically, this question is given to you in such a way, right, that this is a function we don't know how to integrate yet. We might learn how to do this, but yeah, excellent question. Let me show you an example. Sometimes you can't even integrate a thing. Yeah, we'll get back to this. Now, the only thing that I will have to clarify about the question is the other thing you have to have being true is you have to go from like negative number to the same positive number. So if you had like the integral from -2 to 3 of x cubed, knowing that x cubed is odd is not very helpful because these are opposites. But if you have the integral from -3 to 3 of x cubed, you could guess straight up say that's equal to 0 because f of x equal to x cubed is odd. Now, you probably have to show it's odd, meaning you need to show that f of negative x, which is negative x quantity cubed, which is negative x cubed, is the same as negative f of x, which is negative x cubed. So you do have to actually show it's odd, which is what was asked. But it could be super complicated. It could be something like the integral from negative to, let's be careful, James, about your limits of integration there. Let's do this, negative 10 to 10 of sine of x over the square root of 1 plus x squared dx. This function I've just made up is probably impossible to integrate. It looks challenging to say the least. But there's a clue, right? And the clue is that you have a negative 10 and a positive 10 as your limits of integration. So what we're going to do is say, well, I'm hoping that function's odd, right? If it's not odd, I probably just stuck forever. But let's see. So if I call this f of x, just sine of x over the square root of 1 plus x squared, it is kind of vital to remember that sine and tangent and cosecant and cotangent are all odd functions, whereas cosine and secant are both even functions. So f of negative x is sine of negative x, which is the square root of 1 plus negative x squared. Okay, now here's kind of the hard part. Maybe not the hard part, the part that sine of x is an odd function, meaning if you're saying that, if you're saying g of x is equal to sine of x, then g of negative x is equal to negative g of x. So that sine of negative x is in fact equal to negative sine of x. So that's negative sine of x, and the square root of 1 plus negative x squared is just the square root of 1 plus x squared. But look, that's just negative of the function we started with. So this is odd, which means this is equal to 0 since the integrand is odd. In case you, well, I know we graphed sign a little bit, but I really just want to point out, right? Sure. Right, graphically, you can totally see that sine is an odd function. And there's a couple ways to do it, or to think of it. Right, if I graph it like this. I'm sorry, that's not, that's a little bit, it's a little dicey there, James. Okay, looks like that. So there's my very poorly drawn sine function. Yeah, really like the worst kind of. But the point is, right, if you look at f of negative x, that's a horizontal reflection. So if you reflect this horizontally, right, it's going to look like this. Right, this part reflects over there, this part. On the other hand, negative f of x is a reflection vertically. And if you reflect this vertically, oh, it's the same. That's what we're saying. We're saying if a function's odd, its horizontal reflection and its vertical reflection should result in the same looking thing at the end. The red thing there. Or you could say it has rotational symmetry, meaning if you rotate this function 180 degrees, it should look the same as it started. So odd functions, the key kind of property here that we've kind of probably done to death now is that the integral from negative number to positive number of an odd function is equal to 0. Okay, let's look at the flip side of things, which is a little less useful but still useful, is even functions. So even functions have symmetry about the y-axis, meaning that if you flip them horizontally, they look the same. Two good examples of this are y equal to cosine of x, which looks, let's see, here's pi over 2, negative pi over 2. Right, it has kind of this shape. Right, right, so definitely if you flipped it horizontally, it would still look the same as it already did. And then another good example would be, say, like y equal to 4 minus x squared, which looks maybe like this. Okay. So the idea, or the thing we can do with integration for even functions is that, for example, if I wanted to find, say, the integral from negative pi over 2 to pi over 2 of cosine of x dx, I could say, well, it's all this area here. But since there's symmetry, I could try to make my calculation a little bit easier and say, well, really, I'm going to take this part here and then just double it. So this is equal to 2 times the red area, which is just 2 times the integral from 0 to pi over 2 of cosine of x dx. So if you get an even function from, again, negative number to the same corresponding positive number, you can always split it in half and go from 0 to the positive number and then double your answer. So in this case, we'd get 2 times the integral of cosine of sine, it would be sine of x from 0 to pi over 2, which would be 2 times sine of pi over 2 is 1, sine of 0 is 0. To me, and to most people, this does feel a little bit nicer than doing this anymore. You could do it regularly. You say, oh, that's equal to sine of x from negative pi over 2 to pi over 2. And then you have to do sine of pi over 2 minus sine of negative pi over 2, right? So it's a little bit more work that way. Same kind of deal here. Right? You could totally do the entire integral from negative 2 to 2 and get, you would get 4x minus x cubed over 3 from negative 2 to 2. Plug in 2, you get 8 minus 8 thirds. Plug in negative 2, you get negative 8 minus negative 8/3, so plus 8/3, which ends up being 8 plus 8 is 16, and negative 8/3 minus 8/3 is minus 16/3. And 48/3 minus 16/3 is 32/3. But to me, it does feel like it would be a bit easier if we did this instead. So I'm going to take the red area from just 0 to 2 and double it. Right? It's not as nice as with an odd function where you just get 0, but it still is a little bit less work. So I think the even function rule is maybe not as helpful as the odd function rule, but it's still worthwhile. So here we're going to get 4x minus x cubed over 3, from 0 to 2. We plug in the 2, we get 8 minus 8/3. We plug in the 0, we get 0. 24/3 minus 8/3 is 16/3, and 2 times 16/3 is 32/3. Same as we got over there. Okay, so the homework problem you're given is something to the effect of, now it's interesting that in this problem they tell you that we don't know how to calculate the integral, because technically you do know how to calculate it. Let me look back at it just to make sure I'm not lying to you. No, you totally, so here's the example I came up with. We're given that the integral from 0 to 20 of the square root of 400 minus x squared dx is equal to 100 pi. Now I want to point out, you all know how to do this integral. Not because you know how to anti-differentiate this, because we don't, but you know what shape this is. If you have y equal to the square root of 400 minus x squared, what kind of graph does that shape have? Or what kind of graph does that equation have, I guess, is what I'm trying to say. It's everyone's favorite not pointy shape. My wife was watching a terrible TV show that has the name of this shape. It's on Netflix, I think. It's called The Circle. It is awful. And also kind of great, but awful. Anyway, this is a circle. It's actually a semicircle. If you square both sides, y squared equals 400 minus x squared plus y squared equals 400. That's definitely the equation of a circle of radius 20. So technically, you could say, well, look, in fact, I've got the graph. If you look at, let me share my screen again, because prepared stuff, I feel like I should use it. Share my screen. It does most. So let me unclick these. So here's the graph of y equal to the square root of 400 minus x squared. Totally a semicircle. And if we're doing the integral from 0 to 20, we're finding the area that's shaded right there, which is 1/4 of a circle. And I'm pretty sure we know how to find the area of 1/4 of a circle. Right? That's 1/4 pi times the radius squared, which is 1/4 of 400 pi, which is 100 pi. But either way, right, whether or not you know how to integrate this, we can still use the evenness of this function to calculate the other things. And they're asking us to calculate things that would be like the integral from negative 20 to 0 of the same thing. Or the integral from negative 20 to 20 of the same thing. Or then we multiply it by something, right? The integral from negative 20 to 20 of 3 times the square root of 400 minus x squared. I set it 0 to 20, not negative 20 to 20. Okay, in my opinion, this last one is the easiest. This last one, you just factor out the 3. And then you're like, I know what this integral is. That's 100 pi. So this is 3 times 100 pi, which is 300 pi. This one, so the thing that might be a little bit confusing about the odd received, right, is that the even one, the areas cancel out, and the odd sorry, the odd one, the areas cancel out. And the even one, the areas don't cancel, they add together, right? If you look back at the picture, right? If I do the integral from, say, -20 to 0, right? That's got the same area. That's also whatever this, right? This area in black and this area in blue are the same. So if I'm trying to find the integral from -20 to 0, it's the same as the area under the curve from 0 to 20. So this should be the same, meaning this should also be 100 pi. And then if I want the total area from -20 to 20, right, you're really just adding them up. So it's going to be the integral from -20 to 0, which is 100 pi, plus the integral from 0 to 20, which is also 100 pi. So it's going to be 100 pi plus 100 pi, which is 200 pi. So hopefully all that clarifies this even odd stuff, because it can be a bit confusing. Let's see, let me look around here. I have lots of things written down. But lots of questions on lots of things. Yeah, go away. 1 second, I got all sorts of stuff up here. Okay, sure. Ooh. Okay, let's do a few more definite integrals with some u substitution, and then we'll look more at area between curves. Oh yeah, there is one area between curves question that I've seen a few times that's not particularly well phrased, but sorry. Yeah. Let's look at some definite intervals. Let's look at, and I'm gonna maybe change these up just a tiny bit. That's an interesting question. Sure. Let's do the integral from -1 to 1 of 4y plus 5 squared y. -1 to 1, is it a non-function? I don't think it is. You can always check this. So you can ask yourself, is this odd? So I'm going to call this g of y, which is 4y plus 5 squared. I look at g of -y, which is 4 times -y plus 5 squared. It doesn't look like I'm going to get a negative, but it does. I don't think this is going to equal negative g of y, right? Because here I'm just going to get -4y plus 5 squared, which will be 16y squared minus 20 times 2, so 40y plus 25. Whereas if I multiply this out, I'm going to get 16y squared plus 40y plus 25. It's not an odd function. It's also not an even function, because g of y, -y. Oh, I forgot to say what it meant to be an even function. To be an even function, you need f of -x to equal f of x. Basically, the stuff, if you plug in the left-hand number, it's the same as you plug in the opposite right-hand number. So not even, not odd. Most functions are not even or odd. Most functions are neither even or odd. So we want to do this. There's a couple ways we could do it. You could do a u sub, or you could just multiply it out. To me, when the power is the second power, I feel like multiplying out is probably the easier way to go. So I would multiply this out and write it as the integral from -1 to 1 of 16y squared plus 40y plus 25. I don't see a better way to, that's not true. I mean, you could do the u substitution, but it doesn't feel great. Oh, that makes me think. I have a good problem coming up with this. So let's see. So if we integrate this, we're going to get 16y cubed over 3 plus 40y squared over 2, which is 20y squared, plus 25y, -1 to 1. Okay, so plugging in the 1, I'm going to get 16 thirds plus 20 plus 25, minus plugging in the -1, I'm going to get -16 thirds plus 20 minus 25. So the 20s are going to cancel because it's 20 minus 20, but everything else is going to add together. 16 thirds minus negative 16 thirds is 2 times 16 thirds, and 25 minus negative 25 is 2 times 25. So I end up with 32 thirds plus 50, which is 150 thirds, so 182 thirds. Let me show you another example. So again, stop me if you have questions. Let's say we have the integral from, let's go negative 3 to 3 sure, x over the square root of okay. Here's an integral we can totally do. We have to do a u sub though. So what's our choice for u? In fact, let me ask you guys for real, not just asking so I can answer my own question. What would be a good choice for u here? Excellent. Yeah. 1 plus x squared. Great choice for you. The best choice for you. The reason it's a good choice is because then your derivative is there and it's also the separate stuff. So your derivative is 2x, so your du is 2x times dx. So 1/2 du is equal to x dx. All right, so now I'm going to rewrite the integral. I'm going to write it as the integral of, let's see. So x dx is 1/2 du. So that becomes 1/2 du. So you get a 1/2 du divided by the square root of u. Now, here's an excellent question to ask ourselves. Should we change limits of integration? And my usual default answer to that question is probably. It's usually in our interest to change limits of integration. It's especially an interest here. So if x equals -3, u is going to be 1 plus -3 squared, which is 10. If x is equal to +3, u is going to equal 1 plus 3 squared, which is 10. What's the integral from 10 to 10 of 1 over the square root of u? Everybody should be able to answer this question. You all know what happens if you start at 10 and you end at 10. How much area do you get? Exactly. Yeah. So this is so what really happened here, or maybe not what really happened here. Another way you could have approached this problem is you could have said, oh, James, that's actually an odd function. It is odd. You can check. And the integral from negative number to positive number of an odd function is 0. But sometimes you miss that it's odd. That's all right. If you're doing a u sub, it's really going to save you time to sometimes, right? It's not always going to happen. But sometimes if it happened to be an odd function, you do the u sub, you get the limit of integration being the same. You're like, I'm done. The answer is 0. If you hadn't done that, right? If you'd been like, I'm just going to do it the other way where we do the integral. So that's going to be, 1/2. The integral of u to the -1/2 is u to the +1/2 divided by 1/2. The 1/2s cancel from whatever. So then we plug back in and you get u, which is the square root of 1 plus x squared from x equals -3 to 3. And then you plug in the 3 and you get the square root of 10, and you plug in the -3 and you get the square root of 10, and you get 0. That's way more work. We don't want to do way more work. We don't have to do way more work. So a lot of the time, changing limits of integration is going to be a really good idea. I think you should always default to changing limits of integration. Do a couple more definite integrals with some u sub here. Let's see, where'd you go? Sure. Do the integral from 1 to 3 of the e to the 4 minus x dx. This doesn't look too bad. Did I pick? Oh, that's funny. I made it kind of a not on purpose but interesting choice. So, yeah. Actually, now that I see that, I'm going to change this to 0 to 3 to make it a little bit less confusing. So, I don't exactly know what the integral of e to the 4 minus x is. I would probably do a u sum. I'm going to let u equal 4 minus x. And then du is going to be negative 1 times dx. So negative du is equal to dx. So now we start changing things. Dx becomes negative du, which I'm going to write as negative du. Okay, I'm taking care of the dx. And then I'm going to have e to the u. And then I would like to change my limits of integration. So x equals 0, I'm going to get u equal to 4 minus 0, which is 4. If x equals 3, u is going to equal 4 minus 3, which is 1. And then, since my limits of integration are out of order, and especially since I already have a negative sign out front, I can totally rewrite my integral as positive the integral from 1 to 4 of e to the u du. You do not have to do this. I just like to do it, especially if there's already a negative sign out there. That's going to be the integral of e to the u is e to the u from 1 to 4, which is e to the 4 minus e to the 1. And that's your answer. There's no simplifying really. Let's do another one. So I really want to point out with these definite integrals, you have to do a u sub. You do not have to change limits of integration, but I think that's kind of the way to go. Let's look at something like the integral from 0 to 2 of how gross do I want this to be? Not that gross. X squared over, to make it, sure, 1 plus, I don't want to make it that easy. Let's make it 2x cubed. Make it 12. Sure. Here's a problem for us. Integral from 0 to 2 of 1 plus 2x cubed. Sorry, of 12x squared divided by 1 plus 2x cubed. So what do you guys think? Is there an obvious choice for you? Probably. Should I pick you to be the numerator? No. Should I pick you to be the denominator? Yes. 1 because it's in the denominator, but 2, right, its derivative is 6x squared. So it's du is equal to 6x squared dx. And I totally have a 6x squared dx. In this case, instead of dividing by 6 here, since I see 12 has a factor of 6, I might rewrite this integral as the integral from 0 to 2 of 2 times 6x squared over 1 plus 2x cubed dx. And just say, oh, look, there's my du. That's a perfectly legitimate thing to do. If you don't like that, though, you could also just say 1/6 du is equal to x squared dx. And then this x squared dx would be 1/6 du. Either way, you're going to get 12 times 1/6 is going to be 2 du, or you're going to have 2 times du is 2 du. I'll think about that question. Yeah, there's a couple. I can think of a couple examples. We can look at that next year. So, but they're kind of specific. So this is going to become the integral of 2 du over u. And again, we're going to change our limits of integration. If u is 1 plus 2x cubed, when x equals 0, we're going to get u equal to 1 plus 2 times 0 cubed. So u is going to be 1. And when x was equal to 2, u is going to equal 1 plus 2 times 2 cubed, which is 1 plus 2 times 8, which is 1 plus 16, which is 17. Not the nicest numbers ever, but hey, that's life. So then 2 over u, the integral is 2 natural log of the absolute value of u from 1 to 17. So you're going to get 2 natural log of 17 minus 2 natural log of 1. 2 natural log of 1 or natural log of 1 is just 0. So you end up with just 2 times the natural log of 17. Okay. Somebody asked, I think it's a relevant question here. To the person, you can go ahead and write what the question is, and I'll take a look at it and I'll think about that. So, to address the other question, is there a time when? So someone asked, is there a time when u equals the numerator? And there are a couple of examples. One example I can think of is something like this: the integral of, say, natural log of x to the 4th over x. This is totally a time where you want to let u equal something in the numerator. I'm going to let u equal the natural log of x because my du is 1 over x dx. And there's my 1 over x dx. So this would end up being the integral of, let's see, natural log of x becomes u, so I get u to the 4th. And the antiderivative of u to the 4th is u to the 5th. I did this one. Sorry, I did this one as an indefinite. Let's make it definite. Let's say we want to integrate from 1 to, I don't know, 8. Let's make it more. Let's make it e. Let's make it e squared. How about that? So I should change the limits of integration. So if u is natural log of x, x equals 1. U is going to equal the natural log of 1, which is 0. Great. And if x equals e squared, u is going to be the natural log of e squared, which is how much? What's the natural log of e squared? Right. So I get the integral from 0 to 2 of u to the 4th, which is u to the 5th over 5 from 0 to 2. You plug in the 2, plug in the 0. We end up with 32 over 5 minus 0. Another example, something kind of like this. Let me think here. So basically, I would say the kind of examples where you might let u not be the denominator is where somehow the derivative of your choice of the function ends up being something that's in the denominator. So let me see here. We haven't done ones like that. Let me think for just a minute here. Oh, I forgot about the red pen I got down here. I need to mark this part on the floor here. And I dropped the red pen yesterday and got some red pen on the carpet. Not good. Anyway, let's see. Sure, this might not be great, but I'm going to try it anyway. Let's say the integral from 0 to 3 of e to the negative x plus 5 over e to the x dx. Now that's too, the problem, no, that's not a great. So the thing is, you could do a u sub here, but the easier thing to do would just be to divide both things by e to the x. So that is not a great example. Although you could do a u sub. You could let u equal e to the negative x plus 5. Then your du is negative e to the negative x dx. Negative du is e to the negative x dx, but e to the negative x is 1 over e to the x dx. So you end up getting something like that for your negative du. This becomes the integral from, we'll change those, of negative du times u. And then my limits of integration would be kind of terrible. This might be an instance where I wouldn't change them. because my lower limit, if x is 0, u is going to be e to the 0 plus 5, which is 1 plus 5, which is 6. Okay, that's not terrible. But if u is 3, my upper limit is going to be x is 3, u is going to be e to the negative 3 plus 5. Which is kind of gross. When we integrate this, we get u squared over 2, negative u squared over 2, from 6 to e to the negative third plus 5. And then we plug this in. You get negative e to the negative third plus 5 squared over 2 minus 6 squared over 2. That's kind of terrible. I got one more. Yeah, say something like the integral of cosine of the cube root of x divided by x to the 2/3. Let's just do this one as an indefinite integral. So here you could let u equal the cube root of x, which is x to the 1/3. And then your du would be, well, the derivative of this is 1/3 x to the negative 2/3 dx. Multiply both sides by 3, we get 3 du equals x to the negative 2/3 dx. X to the negative 2/3 is 1 over x to the 2/3 and then dx. So right there, there's my 3 du. Just becomes the integral of 3 du times cosine of u, which is 3 times sine of u plus c, which is 3 times sine of the cube root of x. I'll remind you, right, when you have an indefinite integral like this, you have to, what's what we're looking for? You have to plug back in what x is. Sure, I can do, someone asked me if I can do one that's kind of similar-ish to a quiz problem. I can look at one that's similar-ish, but I'm going to make it different. So I want to find the integral from, let's say, 0 to 1 of e to the negative x over, the cube root of e to the negative 2x plus 1. Yeah, that seems all right. Let me ask the person who wrote that. So the person wrote me this. Is your denominator the square root of e to the negative x plus 1, or is it the square root of e to the negative x plus 1? The first one. Okay, that's a little bit different. Yeah. I don't know if I have. Oh, shit. Trying to think. Is that terrible still? Yeah, I'm gonna have to think about how to not do that problem and still help you with it. Yeah. I don't know. Sorry, my brain is. I'm curious about this problem in general. Yeah. Okay. I'm gonna do a different problem that's gonna be kind of similar. It's not going to be super similar, but it's going to give you kind of an idea of how you might tackle this. I'm going to take a look here. Sure, let's do the integral from, I don't really care about limits of integration. Let's see, e to the negative 6x over e to the negative 3x plus 2. This is similar in nature. So this looks kind of wonky, right? You're like, am I telling u equal e to the negative 3x? So that seems like, I don't know, right? If I did that, my du, oh, sorry, I would do e to the negative 3x plus 2, right? And my du would be negative 3 e to the negative 3x. This might actually work, although not in the way I intended it to. Yeah. So if you do it, if you try this, if you try letting u equal to the denominator, your du is this, and you can totally break up the top as. Let me ask this before I get going. And then you can't split up into separate fractions, right? You can only split up into separate fractions if your denominator is a single term and your numerator is multiple terms. Here's what I want to say. Have you guys talked about back substitutions in any of your classes? It's okay if you haven't. I just need to know. No, okay. So the problem is doing it this way when it is going to require back substitution. So let's try something else. We've definitely done problems like this before. There are two ways I can think of tackling it. One way would be, I'm going to do it kind of the more straightforward. So I don't like these negative powers. I'm going to rewrite this as things with positive powers. I'm going to write this as 1 over e to the 6x over 1 over e to the 3x plus 2. So now I'm going to get a common denominator in the bottom, which is going to be, let's see. This is going to be 2 e to the 3x over e to the 3x. You guys good so far? Haven't done anything too crazy? Now I'm going to flip and multiply. This is equal to the integral of, 1 over e to the 6x times the reciprocal of this, which is e to the 3x over 1 plus 2 e to the 3x. E to the 3x divided by e to the 6x, I can, well, e to the 3x, that's 3x minus 6x. So that's going to cancel out 3 of those and leave me with an e to the 3x down there. That seems real dicey, James. So let me double check and make sure I didn't make up a stupid problem. No, this one should work out fine. Oh, I might have made up a dumb problem. Yeah, sorry. It's probably here. Yeah, this is the problem, really? That seems. I don't. Yeah. Yeah. Sorry. This seems like it might necessitate a back substitution. Okay. So here's how I would actually try and do a problem like this. I would let u equal e to the negative 3x plus 2. My du would be the derivative of this, which is negative 3 e to the negative 3x dx. Yeah, okay, I see what's going to happen here. So here's what's going to happen. Negative 1/3 du is e to the negative 3x dx. So I'm going to break this apart. I'm going to write this as the integral from 0 to 1, e to the negative 6, I can break up into an e to the negative 3x times an e to the negative 3x over e to the negative 3x plus 2. This right here, there's my negative 1/3 du. This right here, there's my u. What about this garbage here? Any guesses as to what that might be in terms of u? How could I get e to the negative 3x just by itself? Right, u minus 2. So that's u minus 2. So this is going to be the integral of u minus 2 divided by u times a negative 1/3 du. From not 0 to 1 anymore, these are terrible in this integration. But if x is 0, u is going to be e to the 0 plus 2, which is just 1 plus 2. And if x is 1, u is going to be e to the negative 3 plus 2, which is terrible. But then we can do the thing where you divide each thing, right? So this is equal to negative 1/3 integral from 3 to e to the negative 3 plus 2. U divided by u is 1 minus 2 divided by u. So then we can integrate that. The integral of 1 is u. The integral of 2 over u is 2 natural log of the absolute value of u. From 3 to e to the negative 3 plus 2. Oops. And then you have to plug each of those in. But I think we should stop there. I think that's, there might be another way of tackling a problem like this, but I'm not seeing it. So yeah, that's what I would try, something along those lines for what you guys have there. The key kind of, the way I modeled this problem to be similar to the problem that was written to me is that they're both e to negative powers, and the top power is twice what the bottom power is here. So good luck. That seems like a challenging problem. Yeah, write that one down. Okay, let me do a thing real quick. Oops, oh, I almost ended the meeting for all. Let me cancel that. That's not what I meant to do. Just do that for a second. Okay. All right, where'd you go? That said, I do think we should probably spend the last 20 minutes here talking more about area between curves. I think we did a little bit last class, but I don't exactly remember. So let's look at some examples. Where'd you go? Actually, if you know, a lot of people ask me this question, I do want to make a clarification on this question. So I've seen people ask me to define the area bounded by the following curves. What have we got here? Y equal to 4e to the x over 3. And then we're given y equal to 0, x equal to 6, for example. Now, the way this is phrased is not written very well. If these are just your bounds, here's what we've got. Got y equals 4e to the x over 3, which does something like this. As an intercept at 0, 4. X equals 6, which is this vertical line here. And y equals 0, which is this horizontal line here. Now, I know this isn't what the problem means, but technically, if they say these are your boundaries, you have all of that area, which is an improper integral, which we haven't covered yet. What the problem actually meant, I'm sure, and it's even drawn this way, I think, in your homework, is that it's the area that's in the first quadrant. Maybe it says that and I just missed it, but I don't think it did. So that's the actual area we're trying to find. So if I want to set the integral for this, well, the way I like to think about it, right, is we are adding up rectangles. I mean, rectangles look like this. right? I need to draw all of them. But the area of one of my rectangles is the height times the width. The height of the rectangle is the top function minus the bottom function. So that's going to be, the top function is 4e to the x over 3. The bottom function is y equals 0. And the width of that, of each rectangle, is a small change in x, which is your dx. So then if I want to add up all the areas, right, that's going to be the integral from here to here, right? It's as far left as the rectangles can go, as far right as the rectangles can go. So the integral from 0 to 6 of 4e to the x over 3 dx. Right, I dropped the 0 because I don't need the 0. So then we're going to get, let's see, 4e, what's the integral of 4e to the x over 3? Well, the derivative of 4e to the x over 3 is 4e to the x over 3 times 1/3. So the antiderivative is 4e to the x over 3 divided by 1/3, or times 3, from 0 to 6. Plug in 6, you get 4 times 3 is 12. E to the 6 over 3 is 2. Minus, plug in 0, 4 times 3 is still 12. Times e to the 0. And I would probably simplify this as 12 times e squared minus 1. Let me see. Let me look at some other stuff here. Sorry. Oh yeah, we should do that for sure. Okay. So I was looking to see if you guys have stuff in terms of y as well. I don't know that will quite fit. Okay, so let's look at a few more. But actually, let's look at this next one specifically. So I'm going to find the area bounded by the following functions: y equal to the absolute value of 3x minus 2, x equal to 2, x equal to negative 2, and the y, the x-axis. And I really think when you've got, especially when you got more than 2 things, you really want to draw. So here's my x-axis. Absolute value of 3x minus 2. An absolute value function looks like a V shape, and the bottom of the V is where the insides are equal to 0. So if I set that equal to 0, we get x equal to 2/3. So there's 1, there's 2/3. And my y-intercept, if I set x equal to 0, I get 0 minus 2, but the absolute value of negative 2 is positive 2. So my y-intercept is up here at like 2. So it's looking like this. And then I also have, oops. X equal to 2, x equal to negative 2. So I'm looking at this region here and this region here. What kind of shapes are those regions? Oh, they're triangles. And we know how to find the area of triangles. So here's the deal. Whenever you're finding the area under an absolute value function, the absolute value of just something linear like 3x minus 2 or 5x plus 1 or any kind of mx plus b, you can just say, well, look, I'm going to get triangles. Now I know how to find the area of triangles. The area of this triangle is 1/2 the base times the height. The base is whatever it is from -2 to 2/3. So 2/3 minus -2. That's your base. The height is what you get when you plug in -2. So plugging in -2 to my function here, 3 times -2 is -6, minus 2 is -8. The opposite side of -8 is 8. This triangle, the area is going to be, again, 1/2 the base times the height. The base is 2 minus 2/3. The height is what you get when you plug in +2. 6 minus 2 is 4. So then the area is going to be, let's see, 1/2 times 8 is 4. And 2/3 plus 2 is 2/3 plus 6/3, which is 8/3. Plus 2 minus 2/3 is 6/3 minus 2/3, which is 4/3. So you get 1/2 times 2 is 2 times 4/3. To end up with 32/3 plus 8/3, which is 40/3. So when you have an absolute value area, this is usually what the intention is for Christmas to find it. The idea is just be like, I got triangles, and I know how to find areas of triangles. You can do this in a more complicated way. You can say, well, I know that over here, the function is y equals 3x minus 2. And over here, it's the negative of that. Over here, it's y equal to negative 3x minus 2. So that you can break this up as two integrals. You can say, okay, it's the integral from -2 to 2/3 of negative 3x minus 2 dx plus this area, which is going to be the integral from 2/3 to 2 of this function, which is 3x minus 2. You'll get the same answer, but this feels like a lot more work to get the same answer because I got triangles, I have to find areas of triangles. So I would encourage you to use the triangles if you can. Let's do some more. Find the area between y equals x to the 5th and y equals 2x to the 4th. Often when it's just two functions, you can probably slide by without drawing it. So to find the area between two functions, I need to find where they intersect. So I'm going to set x to the 5th equal to 2x to the 4th. Okay, here's the wrong thing to do. The wrong thing to do would be to divide both sides by x to the 4th. If you divide by x to the 4th, you're left with x equals 2. Which isn't wrong, but it's not all right. You're missing something. Instead, whenever you're solving an equation like this, you have, if it's nonlinear and you have higher powers of x, you almost never want to divide by a variable. Instead, what you want to do is you want to bring everything to one side and then factor. And I may have made a fine choice. You factor out an x to the 4th, you're left with an x minus 2. So then you can say, oh, either x equals 0 or x equals 2. So these functions intersect at 0 and 2. So I don't know exactly what things look like, but maybe right, one of them is, right, they're both getting bigger, right? They're both 0 at 0. And when you plug in 2, they're both equal to 32. So maybe one of them is doing this, maybe one of them is doing it even more like that. I don't know. They probably look totally bonkers. The question really is, which one is bigger on that interval, right? Because whenever you're trying to find the area, again, right, what you're doing is thinking, I've got little rectangles there. And the area of that rectangle is the height times the width. And the height of that rectangle is the top function minus the bottom function. And the width is dx. So how do you know which one's on top and which one's on the bottom? Well, you could graph them both actually and see. But if they just intersect twice, you can say, well, they only intersect there. And in between there, one of them is always bigger. So pick a number in between 0 and 2, and plug it into each function. If I have, for this one, if I plug in, say, 1, 1 to the 5th is equal to 1. I plug in 1 here, 2 times 1 to the 4th is equal to 2. So on this interval, 2x to the 4th is the bigger function. So my area is going to be 2x to the 4th minus x to the 5th times dx. And then my total area, when I add up all the rectangle areas, is going to be the integral from 0 to 2, right? Because that's how far left and how far right my region goes. Sorry, it's not this here, right? It's this stuff in here. And that's my area I'm calculating. It's going to be the integral from 0 to 2 of 2x to the 4th minus x to the 5th. Let me show you some cool arithmetic here, because it is going to help. If we integrate this, we're going to get 2x to the 5th over 5 minus x to the 6th over 6 from 0 to 2. Plugging in 2, you get 2 times 2 to the 5th over 5 minus 2 to the 6th over 6. Minus 0, right? Okay, 2 times 2 to the 5th is 2 to the 6th. I've got a 2 to the 6th here and a 2 to the 6th here. I can factor that out. This is equal to 2 to the 6th times 1/5 minus 1/6. And then it's easier to subtract those fractions than it is to subtract these fractions. 1/5 is 6/30. 1/6 is 5/30. That's going to be 1/30. So I have 2 to the 6th divided by 30, which is 2 to the 5th over 15, which is 32 over 15. That's how much area is in between those curves. Let's see, what else can we do here? Ooh, you guys do have a horizontal one. Let's do that. I don't think I've given you guys this one yet, so let's do, this is one of my kind of go-to problems. I don't think I've shown this one to you yet, but maybe I have. So let's say I want to find the area bounded by y equals 6 minus x, y equal to the square root of x, and y equal to 0. And again, I'm going to draw it. Y equal to the square root of x looks vaguely like this. Y equals 6 minus x to something like that. Has an intercept at 6 on each axis. And y equals 0 is the x-axis. So you have to be a little bit careful, right? We want this region here, not that region there. Because this region here is the one that has each of those functions as one of its boundaries. I want this region here. And I probably want to find all the points of intersection. Specifically this one here. One way to find it, which I'm not going to do, is to set the square root of x equal to 6 minus 6. You can totally do it this way. You can square both sides, solve it. You'll get two solutions. One of them is extraneous. The other way, though, is to say, well, they probably picked something easy. If I try numbers that are easy, take the square root of, I might just get it to work. So let x equals, say, 0. Well, this is going to be 6, and this is going to be 0, because that doesn't work. Let x equal 1. Square root of 1 is 1. 6 minus 1 is 5. No, that doesn't work. Let x equal 4. Square root of 4 is 2. 6 minus 4 is 2. Oh, when x is 4, both of these are equal to 2. That's where they intersect. So a lot of the time when you have like a square root showing up, it's often going to be a number that's easy to take the square root of. All right, here's the thing. I don't want to use vertical rectangles here, because a vertical rectangle means from here to here, the height of the rectangle is going to be the square root of x minus 0. From here to here, the height of the rectangle is going to be 6 minus x minus 0. And so if I was going to do it with a vertical rectangle, I'd have to do it using two integrals. I have to do the integral from 0 to 4 of the square root of x minus the integral from 4, sorry, plus, not minus, don't be crazy, James. The integral from 4 to 6 of this function. There's nothing wrong with that. It's just, I don't want to do the work. Instead, what I'm going to do is I'm going to use a horizontal rectangle. So now the area of that rectangle is, I'm going to say instead of height times width, I'm going to say it's the length times the width. So just like for the vertical rectangles, the height is the top function minus the bottom function, or the bigger y value minus the smaller y value. For the length of this horizontal rectangle, the length is the bigger x value, or the thing further right, minus the smaller x value. So it's going to be the right minus the left times the width, which is a small change in y. So then the right function is y equals 6 minus x, but I have to solve for x as a function of y. So x plus y equals 6, x equals 6 minus y. And the left function, y equals square root of x, if I square both sides, x equals y squared. So the area doing it this way would be the integral of 6 minus y squared dy from my rectangles go as low as 0 and as high as y equal to 2. And that would also work out. If we do it this way, so I would encourage you all to do this one on your own if you have a minute, but doing it this way, we're going to get 6y minus y squared over 2 minus y cubed over 3 from 0 to 2. And we plug in 2, we get 12 minus 4 over 2 is minus 2 minus 8/3. And then we plug in 0, you do get zeros. So this ends up being 10 minus 8/3, which is 30/3 minus 8/3, which is 22/3. If you do it this other way, you should get the same answer.